tip of the iceberg in terms of understanding waves and sound. We don't go too, like we're going to do a little bit more on sound, but there's just like, there is so much to explore with sound and music, with physics. Like, it's crazy. So I'm going to show you one application of this, and I want you to see if you can figure it out. Okay, I don't have my tuning forks yet, I'm getting them tonight, but these are simulated tuning forks. Okay, tuning fork app works just as good. Okay, so this one I've set to go off at 440 hertz, and this one is 449 hertz. Okay, and here's the next one. What do you hear? Can you hear two frequencies going on at the same time? Put it up to the video. Can you describe what you just heard? What's it sound like?
Two wavelengths crashing into each other.
Two wavelengths crashing into each other. Why?
Because they weren't the same, whatever it's called.
Frequency. It's in hertz, so we know it's frequency. They weren't the same frequency. They were only off by a little bit. This was 440, this was 449. So they were off by a little bit, meaning that their waves and troughs were right? And what we actually heard, could you hear it? It was almost like, right? Like a vibration. Those are beats, okay? Not kind of drop the beat sort of beat, but it's a beat when I'll read to you what the definition. A beat, okay? Two waves that add together may have different frequencies. Alternating constructive and destructive interference causes the sound to be alternatively soft and loud. That's why you hear the, okay? This is called beating or producing beats. So I want you to write this down on your sheet of paper, okay? So, like, I know you don't have space on your notes to take out your other paper. So, wave beats. Alternating constructive and destructive interference causes the sound to be alternatively soft and loud. This is called beating or producing beats. Well, if they keep interacting in a way that, like, the crest will interact, and then it will go up.
So there's a time when I won't get the same.
Yeah, there's a time when the crest will interact and cause it to go up, and the troughs will interact and cause it to go down. But it's not completely matched, and it's not completely out of phase. It's kind of in between. So it's that consistently going back and forth and back and forth. Now, this is how people tune an instrument, is because they'll hear that. So they'll strike a tuner, or like a tuning fork, or that you have like a mechanical tuner like this that just makes the right frequency. and then you strike the chord on, say, a piano or a guitar, and you can hear it if you have good ears, right? You can hear those beats resonating, and then so you'll turn your guitar so that it's the exact same frequency, and you know when you've reached it because it sounds good now, right? Because now the frequencies are the exact same. They're vibrating at the exact same frequency, and that's how things are tuned. Isn't that cool? I thought it was cool. No? I show you. So,
Is that physical?
okay, not good. Now,
Actually, that would be physical.
shh, quiet. Exact same. That sounds good. Huh, interesting. Okay. I thought that was exciting when I figured that out. We'll do some more with tuning forks and things like that. I hope that you find it interesting.